In this lesson, we will delve into the reaming and boring techniques within the drilling, boring, and reaming processes and tool applications discussed in Project 1. Boring and reaming play a crucial role in metal cutting processes, as they enhance the precision and surface quality of holes. We will thoroughly explore the principles of boring and reaming, the characteristics of the tools, process parameters, and practical applications. Additionally, we will integrate ideological and political elements to help you understand the importance of attention to detail and striving for excellence in the machining process. In the field of metal cutting, drilling, reaming, and reaming are common methods for hole processing. Drilling is the initial process of creating a hole in solid material, but the precision and surface quality of drilled holes are often low. Boring and reaming, on the other hand, are subsequent processes applied to the drilled holes to enhance their quality. Reaming technology, definition and principles of reaming. Reaming is a method of enlarging an already drilled, cast, or forged hole using a reaming tool. It can correct the axis deviation of the drilled hole and improve the dimensional accuracy and surface quality of the hole. The principle of reaming involves the rotation and feed motion of the reaming tool to remove the excess metal layer from the hole wall. A reaming tool typically has 3 to 4 cutting teeth. Compared to a drill bit, it has more cutting teeth, better guidance, and smoother cutting. As a result, the precision and surface quality of reaming are higher than those of drilling. Structure and characteristics of reaming tool. The structure of a reaming tool is similar to that of a twist drill, but there are some differences. It has fewer cutting edges, typically 3 to 4 shallower chip flutes, a thicker drill core, and better rigidity. The helix angle of a reaming tool is smaller, generally between 10 degrees and 15 degrees, to enhance the strength of the tool. The diameter range of reaming tools is typically between 10 and 80 millimeters. Reaming process parameters. The main process parameters for reaming include cutting speed Vc, feed rate F, and the depth of cut AP. Cutting speed Vc. Cutting speed refers to the linear speed of a selected point on the cutting edge of the reaming tool relative to the workpiece's main motion. The calculation formula is Vc equals pi times d times n divided by 1000, where d is the diameter of the reaming tool in millimeter, and n is the rotational speed of the reaming tool in revolutions per minute. The selection of cutting speed should be determined based on factors such as the workpiece material, tool material, and processing requirements. Generally speaking, when machining ductile materials, a higher cutting speed can be chosen. When machining brittle materials, the cutting speed should be lower. Feed rate. The feed rate refers to the distance the reaming tool moves in the feed direction per revolution, measured in ref. The size of the feed rate affects the cutting force and the surface roughness. If the feed rate is too large, it will increase the cutting force and worsen the surface roughness. If the feed rate is too small, it will reduce production efficiency. Depth of cut AP. The depth of cut refers to the thickness of the cutting layer during reaming, which is half the difference between the diameters before and after reaming. AP equals d minus d0 over 2, where d is the diameter of the hole after boring in millimeter, and d0 is the diameter of the hole before boring in millimeter. Applications of reaming. Reaming is widely used in actual production. For example, in mechanical manufacturing, reaming can serve as the final machining process for holes with relatively low precision requirements. For holes with higher precision requirements, reaming can be a preliminary process before reaming or precision boring. In the manufacturing of hydraulic valves, some holes in the valve body require boring to ensure dimensional accuracy and surface quality, thereby enhancing the performance of the hydraulic valve. Honing technology. Definition and principles of honing. Honing is a method of finishing a roughly machined hole using a reamer. Honing can achieve higher dimensional accuracy and lower surface roughness. Reamers have multiple cutting edges, good guidance, and a small cutting allowance. Therefore, the precision and the surface quality of honing are higher than those of boring. The principle of honing involves the rotation and feed motion of the reamer to perform micro-cutting and extrusion on the whole wall, thereby correcting the dimensional and shape errors of the hole. Structure and characteristics of reamers. Reamers are divided into two types, hand reamers and machine reamers. Hand reamers have a longer working section, providing good guidance and facilitating manual operation. Machine reamers have a shorter working section with better rigidity, making them suitable for reaming operations on machine tools such as drill presses and lathes. Reamers typically have 6 to 12 teeth, which are evenly distributed to ensure the stability of the reaming process. The cutting edges of the reamer have a margin, which serves to smooth the whole wall and improve the surface quality of the hole. Process parameters of honing. The process parameters of honing also include cutting speed Vc, feed rate F, and depth of cut AP. Cutting speed Vc. The cutting speed for honing is generally lower to avoid the formation of built-up edges, which can affect the surface quality of the hole. The calculation formula is the same as for honing. Vc equals pi times d times n divided by 1000. The cutting speed for honing varies depending on the workpiece material. For example, when machining aluminum alloys, the cutting speed can be set higher, typically 20 to 30 meters per minute. When machining steel parts, the cutting speed is generally 5 to 10 meters per minute. Feed rate F. The feed rate for honing is generally larger than that for reaming to ensure proper cutting and chip removal by the reamer. The size of the feed rate should be determined based on factors such as the diameter of the reamer, the workpiece material, and the machining requirements. Depth of cut AP. The depth of cut for honing is relatively small, generally ranging from 0.05 to 0.2 millimeters. If the depth of cut is too large, it will increase the cutting force and accelerate the wear of the reamer. Conversely, if the depth of cut is too small, the cutting edges of the reamer cannot fully function, affecting the quality of the reaming. Applications of honing. Honing is often used for holes that require high precision, such as engine cylinder bores and hydraulic valve bores. In the aerospace industry, where the precision requirements for parts are extremely high, honing technology is widely applied in the machining of holes in various precision components. Ideological and political elements, craftsmanship, spirit, excellence in details. In the processes of boring and reaming, even a slight deviation can result in the hole not meeting precision requirements, thereby affecting the quality of the entire component. For example, the issue of drift during drilling, although just a minor deviation, if not corrected in time, can be magnified during subsequent boring and reaming processes, ultimately leading to the part being scrapped. This requires us to cultivate a spirit of craftsmanship characterized by striving for excellence and meticulous attention to detail during the machining process. We must focus on every detail, starting with drilling, to strictly control the precision of the hole and ensure that every machining step is performed to the highest standard. Taking the machining of holes in an automobile engine block as an example, there are many holes on the engine block that require high precision, such as cylinder bores and crankshaft bores. First, initial holes are drilled into the block. Then, a boring drill is used to enlarge these holes, improving their dimensional accuracy and surface quality. Finally, a reamer is used for reaming to ensure the holes meet the design precision requirements. Throughout the machining process, if the issue of drift occurs during drilling, it may result in the subsequent reaming and boring not achieving the desired effect, thereby affecting the engine's performance. Therefore, during the machining process, workers need to strictly follow the process requirements, conduct a rigorous quality control for each step, and ensure that the precision and the surface quality of the holes meet the standards. In this lesson, we primarily studied the techniques of honing and reaming. Honing involves using a honing drill to enlarge existing holes. The honing drill has multiple teeth and good guidance, which can improve the precision and surface quality of the hole. The process parameters for boring include cutting speed, feed rate, and depth of cut. Reaming is the process of finishing a roughly machined hole. The reamer has more teeth, allowing for higher precision and lower surface roughness. The process parameters for reaming also include cutting speed, feed rate, and depth of cut, but the cutting speed is generally lower and the depth of cut is smaller. Additionally, we emphasize the importance of the spirit of craftsmanship, focusing on every detail in the machining process to avoid minor issues affecting overall quality. Through the analysis of practical cases, we learned about the application of honing and reaming techniques in fields such as automobile engine manufacturing. I hope that in your future studies and practice, you will master the techniques of boring and reaming and cultivate a spirit of craftsmanship that strives for excellence.